Welcome to the 2024 TIDC New England Railroad Symposium, hosted by University of Maine, UConn, and Western New England University. I'm Habib Dagher, Director of the Transportation Infrastructure Durability Center at the University of Maine and Director of the Composite Center at UMaine. The Symposium Planning Committee spent quite a bit of time putting together an excellent program for you, and you could see here the various folks who participated in pulling this symposium for us. Dr. Moshe Shin, Dr. Ramesh Malla, Jim Bryce, Dale Peabody, Aaron Shank, Amanda Collimore, and Jenna O'Barron. The TIDC, or Transportation Infrastructure Durability Center, its mission is to develop innovative, sustainable, next-generation solutions to improve the durability and extend the life of existing transportation assets in New England and throughout the country. And you can see at the bottom of the screen the participating universities in the Transportation Center. So they're the University of Maine, UConn, University of Mass Lowell, University of Rhode Island, University of Vermont, and Western New England University. Partners from the DOT are key to the Transportation Center. They provide an advisory board, and that includes the Maine DOT, Rhode Island DOT, Connecticut Department of Transportation, New Hampshire DOT, Mass DOT, and the Vermont Agency of Transportation. We couldn't be doing the work without the tremendous support we get from the DOTs. Our goal is to make sure that the Transportation Center is responsive to the DOT needs. So the DOTs, oftentimes, they're the ones who actually come up with some ideas, or they review the ideas and make sure these ideas align with the DOT needs. And there's typically a DOT champion on our projects to ensure that the project's eventually results end up being used by the DOTs. The Transportation Center has four thrust areas, and they're integrated. In order to enhance durability, the very first step is to conduct advanced structural and performance assessments, which is what we do. And then the second thrust is to develop new material systems to either fix a problem or to build a new structure. Thrust 3 is advanced structural systems and applications, how to put all these material systems, into a new system that will be more durable is thrust 3. And the last thrust is enhanced performance through innovations in safety, resilience, and connectivity. All these four thrusts are key for us to develop solutions that will enhance the durability of infrastructure systems. I'm going to give you an example of four projects, one in each thrust, that tie to the railroad industry and the railroad needs. The first project I'll talk about is on condition and health monitoring of railroad bridges to evaluate structural safety, integrity, and durability. It's run by the University of Connecticut, and the goal is to develop a method for condition monitoring of railroad bridges for durability and extending the life of the structure. The work resulted in a validated finite element model based on the field tests that were conducted. The finite element model methodology allows users to better understand the global bridge structural performance. And this has the potential to help mitigate structural problems encountered in typical long span and old bridges. What you see on the bottom is, on the left, is a century-old Devon Railroad Bridge that's been studied by UConn researchers and monitored its condition. On the right-hand side is a UConn student with an assessment and monitoring equipment underneath the Coast Cobb Railroad Bridge for this project as well. So this project is leading us to monitoring techniques for railroad bridges and also evaluating, using FEA modeling, their performance combined with the test results. So hopefully a lot of this information can be replicated in many other types of railroad bridges. The next slide is a thermoplastic composite 3D printed tool that we use to produce concrete precast concrete sections, and these precast concrete sections are concrete ballast retainers for a railroad bridge. So basically, they will have ballast inside of them. This project used a 3D printed formwork. And you can see here the formwork in the left photo. It's a 7,000 pounds of ballast retainer formwork that was produced at American Concrete in Vesey, Maine for the project. And the team produced 6 concrete railroad bridge ballast retainers using the 3D printed mold. So they're able to reuse the same formwork, showing that 3D printed tooling can be reused in concrete, and that's in this case it was able to be reused efficiently and effectively. So this could be a good solution for complex sections like this than others that could be produced more readily with a 3D printed tool. And what you see in the right hand. In the center is Professor Roberto Lopez Anidos, who led this program, and the researchers who worked on it. But you can see the scale of these 3D printed tools is fairly large, and we use our large printer at UMaine to produce them. The 3D printed tool was made with a thermoplastic composite mold. And what you see on the right-hand side is one of these ballast retainers being installed on a railroad bridge in Ashland, Maine. Again, this is an example of how additive manufacturing could potentially be used to help with construction of railroad bridges and systems. This third project is about railroad tracks, railroad ties specifically, and pre-stressed concrete ties. As you know, pre-stressed concrete ties can have stress-induced failures. So Western New England University has developed a new concrete formulation using existing material systems, locally available material systems, and non-metallic basalt fibers that increases the strength and the performance of the concrete ties. So they will improve its fracture energy, corrosion resistance, and impact resistance, and can help mitigate failures during its life cycle. What you see on the left-hand side is a sample of a concrete piece used to evaluate the railroad ties using concrete reinforced with carbon fiber strands to reduce the stress-induced failures. The right-hand photo is a microscopic image of a strand bundle investigated to help to reduce stress-induced failures in concrete railroad ties. So the goal of this program altogether is to improve the durability of concrete railroad ties. And the last project I'd like to point out is conducted at the University of Vermont. It's a bridge stream network assessment to identify sensitive structural, hydraulic, and landscape parameters for planning flood mitigation. So if a railroad bridge could be in a floodplain, this tool and this research help us better understand how to build it and where to build it and how to position it. The project developed an analysis method to understand how localized changes at bridges, streams, and roads affect the entire river corridor. And the hydrodynamic models developed under this project have been leveraged to simulate and rank a suite of floodplain reconnection projects that lessen flooding impacts to infrastructure and maximize phosphorus load reductions for the Vermont functioning floodplain initiative. What you see on the left-hand photo is the locations of 14 bridges selected for this analysis on the Otter Creek study area. In the center is a University of Vermont grad student taking stream measurements for the project. And on the right-hand side is a DEM and model cross-section of the Mad River study sections. So these tools, of course, are applicable to railroad bridges, but they're also applicable to all forms of other types of bridges as well. And as you know, here in Maine, for example, we recently have a major storm that devastated our coastal infrastructure, but also devastated infrastructure inland. So as we progress into a global climate change affected world here, these kinds of tools become very critical and important to help assess where bridges can be built, how they can be built, or how they could be raised, and so forth. So And it's my great pleasure to introduce our keynote speaker, session moderator, Jeff Pulver. Jeff is a professional engineer and director of the research and innovation of research and innovation at the Maine DOT. He has been with the Maine DOT since 2018. He worked as an assistant engineer and a civil transportation engineer. Prior to his work at the DOT, Jeff was also a design engineer at Coral Palmer. Jeff has a Bachelor of Science in Civil Engineering and Transportation and Highway Engineering from the University of Maine. He also serves on our Transportation Infrastructure Durability Center's Advisory Board, made up of DOT's leaders from across New England. So with this, please help me welcome Jeff Pulver.